Welcome everyone to the 5th edition of Ekkono's Open Fika. This is our second tech edition, so we will be a little bit more technical and even show you some code. But in the end, you will get to test an amazing demo where we try to predict your next move, and you will be able to play around with the algorithms yourself after that. My name is Rickard König, and I'm CTO and the co-founder of Ekkono. And with me today, I have Thomas Hed, who is a machine learning expert at Ekkono. He will have the second part of this presentation. Some rules of engagement. What? If you have a question, use the chat function. And if you have, and that's for practical questions around Zoom and how to interact with us. If we have a question to me or Thomas, please use the Q&A function and we will answer them in the end. And if you want to comment something during the presentation, please raise your hand. There is a button for that and just raise it and we will be happy to let you in to have a more dynamic discussion. But everyone is on mute, so we unmute you when you raise your hand. So you don't need to say anything before that. Okay, so then let's start this tech edition about incremental learning and predicting your next move. So we at Ekkono do edge machine learning, and with edge machine learning, we mean learning on the edge, and that's not just inference, which is more or less common today if you speak about edge machine learning, but we do incremental learning on the device. And there is many reasons to do that, which we won't go into today, but one of them anyhow is that if you learn on the device, you can learn one model per device, and then you don't need to explain how the device differ from each other. It's enough to explain how what's normal for each device, and that simplifies the machine learning task and make it easier for the models. But to do that, we actually need to learn something from the devices, and the way to do that is incremental learning. And incremental learning differs from the typical machine learning approach, often called batch learning, which starts with collecting a large set of data in a database. Typically, here maybe we have a windmill that we want to do some predictive maintenance for, and we're collecting data continuously over a year maybe. Let's say we want to monitoring the gearbox or the temperature in the gearbox, something like that. When we have enough data, we build a model to minimize some score function so we can really predict the temperature. And when we have that, all this data, we don't need it anymore, so we can just send a trained model to the device and do inference on that. The heavy lifting in machine learning is this training to adapt the model to the data. And since edge machine learning really takes place on microcontrollers that has very limited CPU and memory, this batch learning approach is not really suitable. What's happening? So instead, we at Ekkono focus a lot on incremental learning, which is that instead of waiting until you have a big sample of data, you actually update the model for each instance as it's arrived or as you read it from the sensor. Because then you can adapt over time. In the beginning, of course, the model doesn't know anything, so it can't really guess, and then it will be like a simple moving average, but then as it sees more and more data, it becomes more complex. You may think that this would take a lot of CPU powers compared to batch learning, and I mean, basically it's more or less the same or maybe a little bit less, but here is distributed over time. You just do a few small calculations each time new data arrives, so you don't get any bottlenecks. And on top of that, you don't need to store the data if you don't want to, so you don't have that limitation either. And you can adapt to changes as well if you want to do that. Either you just train for a certain number of hours or days, and then stop, and then you have your train model, or then you continue to train to continuously adapt to your device. So why do we really want to use incremental learning? Well, there's several driving factors. One that is typically frequent is seasonality. If the thing that you monitor is dependent on the season, or typically the ambient temperature, incremental learning is a good thing. If you want to do building automation, the house will work very differently in the summer, in the winter, and machine learning learns from an example. And if you want to do a machine learning model through batch learning, you will need to collect data for a few years to get a real data set that you can actually extrapolate from. So that's one reason, and everything that's corrected to temperature is normally related to seasonality, but there's other factors as well. Then you have mobility, and this is not just vehicles moving around in different environments. It can also be equipment, like rental equipment on building sites, and each building site will have different conditions that will affect the equipment. Another reason is deterioration. If you, for example, want to do some remaining range prediction on a battery, if that is a second or miles or whatever, you will notice that the battery will deteriorate over time. So you will be able to charge it less and less. And that means that you won't be able to have a fixed model. But if the model continuously looks at the usage and the deterioration of your actual device, it can learn from that and keep predicting on an accurate level. And then another reason is also optimization. We work with many machine producers, and they optimize the machines for more or less worst case conditions, because they need some safety margins to be able to ship their equipment, and they do maybe service plans and schedule maintenance based on a very heavy usage, which may not at all be how it's used in reality. But with incremental learning, you can actually learn how it's used today and adapt to that and do predictions based on that. And finally, you also find that machines often need repairs, and parts may change. And if you use batch learning, you would need to stop your prediction, collect data for a new period of time, so you have a representative sample of data, and then build a new model. While in incremental learning, you can just keep training. It won't be as accurate as before, but it will adapt and just need to do small changes. So you don't need to save all the data, you can just continue training. So there's many driving factors for when it's beneficial to use incremental learning. So let's take an example and see how it works. Here we have our Ekkono train, an early version, which is everything is done on a Raspberry Pi 3 here. That's a very powerful platform for us in doing edge machine learning. And the task is here to predict the direction, the yaw of the Pi, 15 seconds, or it's 5 seconds ahead of time. And the yaw is like the compass direction, and you can see the green line here. It goes from 0 up to 360 and down again. So between two peaks here is 1 lap. And we want to be able to predict the direction 5 seconds ahead of time based on 5 seconds history. And we need the history, since you see that some values here are reoccurring. So you can't just look on the current direction to predict it. This means this may seem like an odd example, but it's just a way of getting the data. If you look at the charts here of the data, it's actually very similar to how oil can, the temperature of the oil can vary in a cooling system for some machine. So even if the example is a bit special, the data is rather general. So from this point, predict 5 seconds ahead of time based on 5 seconds back in time. And looking at the graph, we will use this data to predict over here, right? And then we slide this along the graph to learn more. When we do incremental learning, we need to, as in batch learning, we need to do some pre-processing. And in batch learning, it's rather easy. You can just look at it as you're adding a new column in Excel with your new calculations. You can't do that in incremental learning because you can't keep all the data in memory, so to speak, and you need to do it online. And if we take the example we just looked at, the first thing we need to do is to assemble a prediction instance. So if this is our history, here, we don't need to have all the data, but we can have like each third instance here. So if we take each third instance, we get an example. So the task for the incremental model will be from this data, try to predict what the heading or the yaw will be over here. So we need to constantly calculate and update these lags, so to speak. And that's just the prediction. Then it's the learning part. So we also need to assemble a training instance. And since we now in a training instance, when a machine learning model learns, it needs to have the correct answer. And looking at that, so here we know actually what the answer is for this point in time. So then we can backtrack in time and create a training instance with a latest known value as a target, and then fill in with the remaining lags to create the real training instance. So this may seem complicated just for lags, and then you can imagine if you have expressions or moving average and that on top of each other, then it becomes quite cumbersome to keep all this in mind. But we have done, one thing we have done in Ekkono is to have a pipeline, a pre-processing pipeline that help you with that. So setting up this, what we've been just looking at here, you just define which lag attributes you want. You set the target horizon, that is how far you want to predict into the future. And then you can create your model with one line. You give the pipeline and what you want to predict. And doing the prediction, doing all this pre-processing and training the model and making a prediction is just done in one line. Here we add the new yaw that we know, and everything else will be calculated for you. So it's quite neat way of handling this. If we compare incremental learning to batch learning, the downside of incremental learning is that we can't assume that we know the distribution of the data. So we need to make guesses. So what this chart shows is the yellow part here, that's marked in yellow, that's data used to train a batch learn model. And that model is, the prediction of that is marked with orange here. The green is the real value. And you can see, you don't even see the orange graph here. You see it a little bit here and here. So it makes a really good job on it. You can see that it starts here with predicting 0 for a while, and then it starts doing predictions. And that is because it needs to wait until the pipeline is filled with data, until it can start to make the predictions. But here it's trained, so it does that more or less perfect. And then you can see that it also generalizes into new data. The blue one here is the incremental learner. And to start with, we can see that, yes, it needs to wait actually a little bit longer than the batch learning, because here you also need to wait until you know that the target, the horizon as well, since you need to wait until you get a whole training sample until you can start training. So, and then it just guesses the last known value, and then it starts to become even worse. But then here on the third lap, you see that it's actually started to learn, and the fourth lap and fifth lap, then it's really the same on average as the batch learning. So it's quite neat. Often you wonder how much data do you need to learn a concept, and it's definitely often less than what you think, but it also depends on how repeatable or how noisy your data is. So then the question is, what happens if a change occurs? And in this case, we add 2 straights on this track. And as you can see, the data, when it comes in, it's exactly the same. But here is where the first track comes in. It goes in the same direction a longer time, and then it goes down a longer time here as well. And then it's the same again. So it's a very small deviation in the data in the whole circle, but it will have an effect on larger time frame, because it both relates to the pipeline and the predicted value. So if we take this change and continue to run both the same models, we see that, okay, here is a change. They work similarly good. And here suddenly the batch learn model, that is the orange one, totally goes bananas. The relationship it has learned is not there anymore. It's just this small deviation has thrown it off track. So it doesn't work at all, and it never recovers. Looking at the incremental model, you see that is also way off here, because it's the time dependence is not the same for the first one. It's quite far from here to here as well. But after just one lap, it starts to find it again, and 2 or 3, it's all the way back. So that's typically how we work with incremental learning. And now Thomas is going to show you a demo of this, and we're going to see if we can actually predict your next move. Because after Thomas' walkthrough, you will get to try it out and see how random you actually can be. So take it away, Thomas, please.
So just figuring out how to unmute my microphone. So this is the demo. I hope you can see my screen now. You can find it here at demo.ekkono.ai. And well, it's very simple. It's just 2 buttons here. Well, it's 3 actually. You get the 1 and 0 to click on, and you get this help button, which shows you a little bit information, which is the same that you get when you enter the site on the first time. We get here random forest. It's which algorithm we are using. And also you get an instruction to press the buttons 10 more times to set up. And that is, like Richard said, to fill up the pipeline. So we have a memory of 10 clicks. So I will click here, I click on the buttons. And also if you're on a computer you want to play, you can use the keyboard, the 1 and the 0 on the keyboard, and just click that. And then we filled up the memory, and the system starts to predict what you're going to press next. This time I pressed 1, and the system expected me to press a 0, so the accuracy is 0. I pressed 0 now, and well, that was correct. That was what the system expected me to do. So then the accuracy increases. And as you can see, as I go on here, the accuracy was changed. I'm really being odd right now because I get a low score. And as I click more and more, the incremental algorithm gets better and better on predicting what I will click next. So now I clicked 100 times, and I know that because here in the lower corner, I get some kind of faucet, the correct answer. And it says here, I pressed 1, and I expected you to press 0. And in the next prediction, in the next click, I expect you to press a 1. And you can see here, if I press 1, then the accuracy will go up. And if I press the other button here is 0 prediction, I press 1 again, then the accuracy will go down. So you can see here that we are not hitting. And as I continue, it hopefully gets better and better at predicting what's going on. And I thought I would show you here what is behind the scenes of this. So this is the architecture of the system. We have the AWS in the bottom with a Docker container, and hosting for the web is Nginx. And on the other side, we have the .NET Core implementation of our SDK then. And the Ekkono SDK comes in many flavors, C#, Python, and C++. So in this case, with the .NET Core, I use the C# implementation. And the code behind this is really simple. It's just a bit simplified here, of course, because I validate data and so on. But it's just set up a model, configuring the inputs. In this case, we have only one attribute. It's what you're going to click, the 1 or a 0. So it's a long list of 1 and 0s, and I call that input. You can call it anything. Then you set up your attribute vector with this only attribute then. You set up a pipeline, like Rickard talked about earlier. And then finally, you create the model. This is just a one-liner, and you're ready to go. And the pipeline, as Rickard told you about the lags. And at this point, we are setting up 10 lags for the system. So we have a memory of 10 clicks backwards. And then we have set the target horizon for 1. So we are predicting 1 step into the future. That's the next click we are predicting. So this is the only thing you need for setting up a pipeline. So to make an example here, if I press 1001, 1001, 11, then that is our input here. And the lag is really simple. Like in the third one here, you have a lag 1 for the previous. You have the lag 2 for the one before that, and 1 for the one before that. You understand? We have a lot of ways to create things in our pipeline. We have the lags, we have moving averages, we have deltas, we have expressions, and so on. And the pipe is, you put your variable down in the top, and the pipeline creates all the other things for you, and it comes down in the bottom with many things. So in this example we have here on the demo, we are using the following things. We have a 3 moving average, like the average of those 3. We have a moving average of 5. The last 5 is an average. We have a delta 1, 2, and 3, and that is 1 step back in the future. We take the difference between those. And delta 2 is 2, we take the difference of those. And 3, of course, is the difference of those. And to set up the moving average and the delta attributes, this is the only thing you need to add in your code. So we first have the 10 lag attributes, then we have 2 moving averages of 3 and 5, and then we have the delta attributes of 1, 2, and 3 backwards. We set the horizon to 1, and then we're off. And when that is done, we just need to do the prediction. So we get an input, what have you clicked? You clicked 1, we put that into a double array, send that into your model, and you get a response. What will I click next? So if we look here on the site also, we have a cogwheel. You can make some settings. You remember I told you there's a random forest in the background here. We also have linear regression and the neural network, which you can also use. And for each of them, if you don't know a lot about those, then we have the theory section here. You can read about the random forest. You can read about linear regression, which is basically to fit the line to a known number of parameters. And you can also look at neural networks, which is basically a series of linear regressions in different layers. And then you can change the settings. So now I changed the settings to a 3-layer with 10 neurons in the first layer, 5 in the second, 3 in the last. Press OK, and as you can see here, well, we changed into a neural network, and the counter is reset. And now, as I go on clicking, then the neural network is used instead of the regression tree, the random forest. And so, if we look at the statistics on the site, I know you're all statistic nerds like we are. We have had this site open for a while, and 42 of you actually did 100 presses. 26 of you continued to 200. There was one single person who made it up to 1,200 presses, and I didn't add it here. But as you can see, we have after 100 presses, then it's 35% minimum and 93% maximum, which prediction rate we have. And the average is 57. And the more information the system gets, the more precise it gets. You can see the minimum value here after 400 is above 50% on minimum. And we keep to around 60-65% in the prediction. So we are a bit better than random. Yeah, and that was the demo. Do we have any questions? Let me see. How do I see that? Oh. Rika, do we have any questions? No.
No question in the Q&A.
Yeah, no questions. No. Okay, that's good. Oh, I saw. Well then, I'm messing up my slides. We have a next session in Thursday in 2 weeks, because next week is Valborgsmässoafton. So I will see you guys in 2 weeks' time in the next session. It's about energy efficient algorithms. You can find us on social media, and also you can find the sites we just demo on demo.ekkono.ai.
Yes.
So thank you very much for today.
And please go in and see if you can beat the machine learning here, or create a better model by changing the settings there. You can be your own machine learning expert if you're not that already. Thank you so much for joining, everyone.
Thank you.